We've already learned how to take the derivatives of trig functions like sine, cosine, tangent, etc. But we have not looked at inverse trig functions. And before we find derivatives of inverse trig functions, let's just remind ourselves what inverse trig functions are and what they look like. So we could look at inverse sine. So we remember that this is written inverse sine of x. Sometimes this is written arc sine of x. And just a few things, we remember that notationally, this is kind of a bad notation on the part of mathematicians, is that sine inverse, when it's written like this is not the same thing as saying sine of x to the -1. Or 1 over sine of x. Those are not the same thing. So notationally, this is bad notation. If I write sine with a -1 like it's written up top, that is not 1 over sine. That is the inverse of sine. Kind of like natural logs are the inverse of exponential functions. This is the inverse of the sine function. Okay, so just make sure you're careful of that. Don't try and rewrite this and use a quotient rule on it. That is a bad idea. That's why I kind of prefer this notation arc sine, arc cosine, arc tangent, because it solidifies that idea that these are not equal to 1 over the trig function. But we'll use both notations because mathematicians use both notations and you need to be comfortable with both. So this is the inverse sine. If we remember, what does it mean for y to be equal to inverse sine of x? This is the same thing as saying that sine of y is equal to x. So y is the angle and x is the output that we get. So we could say something like, what is inverse sine of 0? Well, let's say inverse sine of 1 because that's a little more interesting. So we're asking what angle gives us sine of that angle equals 1. And if you remember from trig, the angle that gives you 1 out for sine is pi over 2 if you're thinking in radians, or 90 degrees if you're thinking in degrees. For calculus, we are always thinking in radians. So if you think in degrees first, you must convert that to radians. Okay. We remember from pre-calculus that the inverse trig functions, we have to restrict what y values, what outputs we can get, because otherwise we can't actually find inverses. This is not something that's super important for us in calculus. But for sine, we get values between -pi/2 and pi/2. Cosine, we get values out that are between 0 and pi, and then tangent is the same as sine, except for we don't get those endpoints because tangent is undefined at pi/2 and -pi/2. Okay, so that was like a really quick overview of inverse trig functions, but the most important part for taking derivatives for inverse trig functions is this relationship. And we're going to go ahead, I'll use implicit differentiation to show you how we find the derivative of inverse trig functions, and then we can scroll down and look at the table. So if I'm looking for the derivative of inverse sine of x, what I'm going to start out by doing is doing what I've done up here. So let's write that y is equal to inverse sine of x. So what we're really looking for here is dy over dx, since this thing was equal to y with my notation. Okay, well, yeah, that doesn't help us, right? But if we rewrite this expression as sine of y is equal to x, then we can use implicit differentiation on that. We know how to take the derivative of sine and we know how to take the derivative of x, so implicit differentiation will work nicely. The derivative of sine is cosine, and because there's a y there, we're going to get a dy dx here, and then that's equal to 1. And so if we solve for dy dx is 1 over cosine of y. Well, that's exactly what we were looking for. We were looking for dy dx. So this would be our answer, except for the fact that this answer has y in it, and our original expression only had x in it. So that's kind of messy. Why do we want to give our final answer with y when we started out with x's? So let's see if we can figure out what cosine of y is in terms of x. Okay. So we know that sine of y is equal to x. And we can use what should be your favorite trig identity, is that sine squared plus cosine squared is equal to 1. Okay, well, sine was just x, so we could replace sine squared y with x. And we can subtract x squared from both sides. And take the square root of both sides to get that, to get that cosine of y is 1 minus x squared under the square root. Okay, you're not gonna have to recreate this, but hopefully you see where that's coming from. So we can replace cosine of y with square root of 1 minus x squared, and that is our derivative of inverse sine. Okay, so the nice thing to notice here is that implicit differentiation works really nicely to get us the derivative of inverse sine. And then we have to use a trig expression so that we get that final answer in terms of x. But I'm not going to ask you to recreate this every time. It's good to know where it comes from, but you don't have to recreate this. So you're going to want to memorize this. Once again, I don't ask you to memorize too many things, but this one is useful to memorize. And you can do the same thing to find the derivatives of all the other inverse trig functions. It follows pretty much the same, so we're not going to do that. I'm going to ask you to memorize these three, the inverse cosine, inverse sine, and inverse tangent, but I've given you the other ones over here just so that you have them as well. Notice that the difference between the derivative of inverse sine and inverse cosine is just a negative. Inverse tangent doesn't have a square root and it has a plus in the denominator, so it looks a little bit different. Okay. One fact to notice is that when you take the square root of both sides, you should technically get plus or minus. So we should really be getting a plus or minus square root here. The way that we're restricting the domain and range is actually what allows us just to get a positive square root. So this is kind of a small detail to include there, but once again, not something that you really need to know long term, but something good to like just have in the back of your mind. Okay, so now we've kind of done some messy work, but now to use these derivatives, it's nothing more than like mixing them together with a product rule, a quotient rule, a chain rule, and memorizing 3 formulas. So the biggest thing you want to do tonight before class tomorrow is memorize these formulas. But let's get some practice taking derivatives using them. So this first one looks like it's going to use a quotient rule. You should try it on your own first. So if I use the quotient rule, I'm going to have low times d high. Well, the derivative of inverse sine is that thing that we just calculated, 1 over the square root of 1 minus x squared, minus high d low in this case is just 1 all over low squared. Okay, that one was really just a quotient rule and then using one of these formulas above. Okay, once again, try these on your own. Arctangent, same thing as tan inverse, so we're going to be using this guy. We're going to need a product rule here. So the derivative of x, we've got this piece and this piece. The derivative of x is 1. We leave the arctangent alone. Then I leave the x alone. And then the derivative of arctan is 1 over 1 plus x squared. Okay, cool. We're chugging along here. Inverse cosine of 2x, we're going to need a chain rule. My outside function here is inverse cosine of x. My inside function is 2x. The derivative of inverse cosine is negative 1 over square root of 1 minus x squared from the box above. The derivative of 2x is just 2. When we put these back together, we're going to plug the 2x in here. So we're going to get negative 1 over root 1 minus 2x squared. Make sure you put parentheses around that because both the 2 and the x are getting squared. And we multiply that all by 2. Okay, so hopefully the takeaway from this should be that you have 3 formulas to memorize for class tomorrow. Inverse trig derivatives, we're just really mixing these with all the other rules that we've learned once we memorize those 3 formulas.